Suppose you had each of the four functions presented to you, and you were being asked to take the derivatives of the following. So please pause the video and see if you can find the derivatives of the four following problems. Here's the work for the first. We could expand the entire thing and then take the derivative of each piece. So f prime of x equals 8x plus 20. Here's the work for the second. Once we've expanded it, then we can find the derivative, and we would end up with 24x squared plus 120x plus 150, which should give us some concern for the next one. We could use the Binomial Theorem here in red to help us speed up the process of expanding, and once we multiply everything out, we would end up with this function, and taking the derivative using the power rule, we would end up with this function. Finally, if we attempted to deal with the fourth function, the best we could do is rewrite it with our current tools as f of x equals 2x plus 5 to the 1/2 power. There's not much we can do with that given what we currently know. So 3 of these are possible, although kind of a pain algebraically, and the fourth one we cannot approach, which is why we need to learn what's called the chain rule. So the chain rule takes this approach to what we're doing. We have a function that's made up of multiple parts. It's a composite function. So broadly speaking, we're looking at something like a function y. Let me do that in a different color. Y equals f of u. It's a function with some input, and that input is a function itself. Alright, what we mean by that might be something like if y equals z squared and z happens to equal 2x plus 5, then y is equal to 2x plus 5 squared. Right, that's how it relates to what we were talking about initially, and we want to know what is the derivative of y with respect to x, and in order to do that, we're going to consider, again we're speaking technically here, the derivative of y with respect to z, and the derivative of z with respect to x. Notice that these are equal expressions. Right, so that might be the technicality of it. Or if we use function notation, we're taking the derivative of a composite function, and that composite function is f of g of x. And when you do this, you're going to take the derivative of f of g of x, again just using some function notation, times the derivative of g of x. So this is all the formality of it. But let's break it down in another way. Maybe use some less technical language. F of x equals 2x plus 5 squared. And we've already found that by expanding this. We found the derivative by expanding it, but we can use the chain rule as well. So by the chain rule, the way I like to think about it is I'm going to take the derivative of the whole thing. So in this case, I can use the power rule on the whole thing. I'm going to bring the 2 down and multiply that by 2x plus 5, which is the base, to the first, decreasing the power by 1, and now I need to multiply by the derivative of the inside. The inside, in this case, is 2x plus 5, and its derivative is 2. So here's the derivative of the outside times the derivative of the inside. Be a way to talk about it. And notice when we clean this up, we end up with 4 from 2 times 2 times 2x plus 5, which is equal to 8x plus 20. The exact same derivative we had gotten using by expansion. And this is all fine and good, but it becomes really helpful as a much quicker way to find the derivative of f of x equals, say, 2x plus 5 to the 6th. We've already found that by expansion. But now we could use the chain rule. So I'm going to take the derivative of the outside using the power rule. So 6 times 2x plus 5 to the 5th. And now I need to multiply by the derivative of the inside, in this case 2. This leaves me with 12 times 2x plus 5 to the 5th. This, if we were to expand it out, is the exact same answer we got originally. But this is a whole lot cleaner and a whole lot faster, more efficient as well. So in principle, the idea behind the chain rule, another way to talk about it might be take the derivative of the entire piece and then take the derivative of the inside. Let's consider how this would work with f of x equaling the square root of 2x plus 5, which we know is equivalent to 2x plus 5 to the 1/2. Well, by the chain rule, we'll take the derivative of the whole thing using the power rule in this case. So 1/2 times 2x plus 5 to the negative 1/2. Now we need to multiply by the derivative of the inside, which in this case is 2. And when we clean this up, we find that the derivative is equal to 2x plus 5 to the negative 1/2 power, or 1 over the square root of 2x plus 5. Let's look at a few more examples. Here's example 6. If I want to find the derivative by the chain rule, I'll take the derivative of the entire thing, in this case using the power rule. So it'll be 3 times the base with the power decreased. And now I need to multiply by the derivative of the inside, in this case 6x minus 2. And I'll clean this up just a little bit. I'll do 3 times 6x minus 2, which gives me 18x minus 6 times 3x squared minus 2x plus 1 quantity squared. A lot of times there's no good reason to even clean it up, and it's fine to just stop here, but there are cases where it would be beneficial to clean things up a little bit. And that just comes with experience, knowing when. Let's consider example 7. Y equals 7 minus 4x squared to the 2/3 power. The derivative by the chain rule is to take the derivative of the whole thing. So bring the power down by the power rule, 2/3 times 7 minus 4x squared. Decrease the power by 1 to the negative 1/3 power times the derivative of the inside, in this case negative 8x. This I'll clean up a little bit. This is negative 16x over 3 times 7 minus 4x squared to the negative 1/3. One last example. We've got y equals negative 2 over the 4th root of 6x minus 1. Now I could use the quotient rule on this if I wanted to, because it is the quotient of two things. But if I wanted to use the chain rule, I would change this to... Actually, no, I'm going to use the quotient rule to get started. So this will be the derivative of the numerator, which is 0, times the denominator, the 4th root of 6x minus 1, minus the numerator times the derivative of the denominator. And the denominator is 6x minus 1 to the 1/4 power. And I'll need to use the chain rule here. So this will be 1/4 times 6x minus 1 to the negative 3/4 power times the derivative of the inside, which is 6. And this whole nasty thing is over the denominator squared. So the 4th root of 6x minus 1 squared. I'm going to clean this up just a little bit. Y prime equals, well, 0 times the 4th root is going to be 0. I've got negative 2, which is 2. That can be multiplied by a 4th to get 1/2, and 1/2 times 6 would be 3. So the numerator can become 3 times 6x minus 1 to the negative 3/4 all over. We've got a 4th root squared, which is the same as 6x minus 1 to the 1/2 power. And I can clean this up just a little bit more by bringing this piece down, and I'll end up with 3 over 6x minus 1. And when I bring that 6x minus 1 to the negative 3/4 down, I end up with 5/4 as my exponent. And this problem in particular highlights this idea about calculus, that it isn't the calculus that's hard, but it's the algebra that can be confusing. So there you have some application of the chain rule, and there will be one more video with some more examples of the chain rule.